In this next section, I'm going to show some VASP sample jobs, which really showcase some of the science that can be possible with VASP running on NERSC Perlmutter, and some interesting research cases that NERSC users have run on Perlmutter that demonstrate, what can be done. And so you may have jobs that are similar in size to some of these, and these give you an idea of the amount of resources that you might need and the amount of time it may take to run them. So first is the materials genome. In this job, we have MOFs, which are composed of two major components: a metal ion or cluster or metal ions, and an organic molecule called a linker. This example illustrates a structural relaxation that has many atoms and many bands and large FFT grids. So you can see 3,500 atoms, 9,600 bands, and then FFT grids that are in the hundreds. For this particular job, this completed 99 ionic steps in about 33 hours using 32 GPU nodes, which is 128 GPUs on Perlmutter. The next case is from the Discovery of Materials for Energy Applications project. By tracking the trajectories of lithium atoms, the mean square displacement and further diffusities can be evaluated. And ultimately, the goal of this project is to learn if amorphous VF3 is a good lithium conductor or not by comparing this with other benchmark materials such as lithium iron phosphate. This particular example is one that illustrates a relaxation with many atoms and also many K points. You can see that this has 777 K points, which gives you an irreducible number of 172 K points. So this is an example of a job in which the K-par parallelization would be very useful. In this case, the job took 66 ionic steps and completed in about 17 hours on 160 Perlmutter GPU nodes, or 640 GPUs. In this third test case, we're simulating coarse level spectroscopy of energy relevant materials. And this job is a photon calculation using density functional perturbation theory. And this photon calculation is similar to a frequency calculation for molecules, which involves computing second derivatives of the potential energy surface with respect to displacements. So this is a more challenging type of calculation than a simple energy evaluation. This kind of job used large FFT grids of 108, 216, and 432, and this took 37 hours to run on 27 GPU nodes. Finally, we have this calculation on this bismuth molybdenum nickel system, which is an alloy system used for catalysis to reduce methane to carbon. It's believed that at certain temperatures, this liquid alloy system may form some cluster, which could help the catalytic properties. This is an example of a VASP calculation on many atoms, in this case, 864, with a very large number of molecular dynamic steps. In this case, we have 3,000 molecular dynamic steps, which runs in 43.3 hours on 64 Perlmutter nodes. And this gives 52 seconds per MD step. So if you have a similar size system, you may expect a similar number a similar amount of runtime per step.